So first things first, not football. GTC is coming to Europe. Have it in mind, 9th to 11th of October. If you want to have some early pricing, you can use one of those keys. You find many of those, and there are also attractive offerings for students. So everybody is interested in deep learning, applied deep learning, learning more. Welcome.
And for your information, we are of course at the GTC.
Of course you are there.
Yeah. So we will be also there as IEM.
Perfect. So one of the main use cases, self-driving cars, everybody talks about it. And the problem is really one of the hardest problems I've ever seen. And there are a lot of things to do. Of course, collecting data, because AI is all about programming by means of data, right? We need to train the models, but the data we get is not complete, so we need to do a lot of simulation. We also need to do simulation by creating artificial worlds, because taking the BB-8, we have 2 in Germany of those, and basically creating a scenario where you drive at 100 kilometers on the Autobahn, but with a 2 meters distance, because you want to have that special situation to understand if your systems are behaving correctly, does not work. So we cannot create every situation and recall it with live vehicles. So because we would violate traffic rules. So it's a huge amount of processing necessary. So we're happy that we have partners who jump on that AI and HPC train with good offerings. Think about in a car, there are a lot of things a car has to understand. Traffic signs, is the road ahead, is it free? Is it drivable? Is this a lane marking? So there are a lot of different things. And overall we count with at least 10 neural networks which self-driving car manufacturer has to develop. That's kind of roundabout. Some mix the functionality when they've developed them together, so they reduce the amount of networks they have to deploy. But overall, we try at the moment to solve each aspect individually, because then we have no side effects from another network and we can really drive it to the maximum. So the typical way we design it is that one network has 2 purposes, because we want to have redundancy inside. So if one network does not tell us the truth, we at least has a second ground truth, which might us think about, is it the right one? So we have no second result. So it's all for built-in redundancy. There are nice recordings about this one on YouTube, but I want to get over it quickly. So deep learning, artificial intelligence, it's a cycle. There are a lot of things you want to try. And I don't agree fully with Stephanie to say it's so sophisticated. Of course, our customers drive it to the maximum, and it gets sophisticated the longer you do it. But if you want to start, I think everybody in the room can start. And there are a couple of lazy ways to jump into, but it's an iterative cycle. So let's say we take one of our BBAs, we collect some data, and you can do the math. We have it on the road 200 days a week, 200 days a year, kind of 8 hours. Well, this vehicle at the end of this year has collected 1 billion images. That's a huge amount. We need to filter it. You don't want to feed 1 billion images into your GPU. It would not end at the time you want to have it. But it gets a lot, and you're not having just a single one on the street. You want to have, at the moment we have 12 growing, but some other vendors, I think Ford has 100 out. We're not a vendor, by the way. It's a technological challenge for us. We want to be the robotics platform of choice. So this is why we're doing this exercise. It's not about bringing self-driving cars to market by us. Training comes next. We develop some networks, but then do we have the right data? Maybe not. Maybe we've collected too much data, which is basically too friendly for the AI, which is not challenging. Let's say the road is straight. That's boring, kind of. You need to get more entropy inside. So you have to understand that at some, is this scenario covered? Do I have a scenario which is, for example, turning with a low sun disturbing my my LiDAR, because it's also affected by low sunlight and reflection. Then my cameras. So you start to develop challenging situations. And just some data on this one. This one you can see two basically things like this. Those are the LiDARs. They are they're a bit looking downwards to have a more complete picture. And this system has 12 2-megapixel cameras. This is basically a generation before. There's another one with higher resolution. But this explains the amount of data which is coming in. 12 cameras at 30 frames per second with 2 megapixels each. That's a lot of data. And then you're adjusting. A neural network is full of hyperparameters. You don't need to make it sophisticated at the beginning to start, in a more simpler case, when you really want to get your hands on. But at the end, when you drive it to perfection, this is basically something you're going to do. Then, what a lot of people don't really see at the moment, the networks, they are basically made lighter, so to say. There are a lot of weights which you can then get rid of. You can also reduce the precision. Sometimes it has a little penalty on the precision of your entire network, but in the car, the inferencing has to go quick. You don't want to wait because you need real-time decisions. So the network has to be fast, lightweight. A lot of networks we use today are not that lightweight. Then you test it, but it goes separate iterations. So it's a huge amount of work, a huge amount of data which has to be carried through the system. So in order to find results quickly, we basically learned the following. We act in a sprint manner. We have small experiments, and a couple of, let's say, the first 2 rows in this room compete against and say, I'm going to make this network better. And then they develop their ideas, and after 2 days we say, okay, which 5 candidate wins? And then we take basically the big one in a development phase, so we made the experiment bigger. And we take the winner out of this one, then we basically tune the hyperparameters. And this basically defines the next step for 2 weeks later. Who's developing neural networks? Hands up. Who wants to develop neural networks? It's super easy. You go on GitHub. I'm serious. There are 2 ways. You can read a lot of books, and then you find out, I don't understand how this relates with this, but you understand it very quickly if you go to do it in a hands-on manner. Everybody, who knows Coursera? Hands up. Who uses Coursera? Okay, could be more. Udacity? So Coursera, easy way to get hands on the technology, a good way to getting it taught. I can recommend it to everybody. It's really great, and everybody can do it. Okay, I think I've said enough. It's sophisticated. So we need a lot of horsepower, but Moore's law lets us down. And actually, the blue line is basically what Moore's law has given us, but it stalls. And kind of 10 years back, we developed CUDA, which is a parallel programming paradigm with a parallel architecture. It's limited to computation, so it's not a full-blown processor, but it has its purpose and its very strength in this one. And the community trusts in us that we drive this thing forward, this line. So, so far we proved to our users that we are able to scale linearly. But that's not enough, we need even more. We have 1 GPU which is highly parallel. Stephanie told about the IBM system, which is also parallel, 4 GPUs. We have an own product line, there are 8 and 16 inside, but even that's not enough, so we stack and rack it up. This is a picture of a Saturn V. This is our own development system, and we have more than 660 of those boxes inside, and round about 100 are used for the team which is doing the the training for self-driving cars. So it's a huge appetite, and we have a luxury situation, so to say, because we are producing them, so that might explain why we have that much, but we use it for a lot of other development purposes as well. I want to go to multi-GPU now and be a bit more technical. So, hands up, who did TensorFlow training with a neural network? How many GPUs did you use? 1. 4. You're welcome. How did you do it?
I used Keras with TensorFlow as the backend, and there it's pretty easy to train multi-GPU.
So when you basically kicked off the training code, you told Keras to use 4 GPUs?
Yeah, it's a function.
Yes. This is a good way to start. It's not the optimal way, because this is an architecture of one of our platforms. I come to the IBM architecture quickly, but the green one are NVLinks, and the green boxes are the GPUs. So in that system we have 8 of those, and the gray one is the passes to the PCI. So when we do training, when we use 1 GPU, of course it's easy. The CPU feeds the data into the forward pass, it gets processed, and then we do the back propagation. So that's basically, there's nothing special. But when we want to use all of them, they have to coordinate in some manner. So if you're building a wall, it's easy. We can basically line up. We don't need to talk to each other. We can finish the wall without talking. Here, we do the following. Every GPU gets the same task. So your model, what you developed, will be instantiated here, 8 times. But they're getting different data. So this is called, same model, but data parallelism. And now we know that it's a numerical optimization process, and they're doing a gradient descent. So at the end, when you start to do the backward pass, you want to optimize the situation with the difference you've learned. But if everyone does it in a different way, you don't have any benefit. So you need to sync. And the weights or the gradients, this one calculated in the forward pass, you're going to tell every other one to use it, because you want to do an all reduce over all the gradients. So this one has to know what the gradient of this one was, and each other has to know. So this is basically a communication problem. If you do it in the Keras way, then, forget this for a moment, you told you had 4 GPUs, then the CPU is basically collecting gradients of GPU 0, 1, 2, 3, and averaging all of those. So that they have the same tensors, you basically add them together, divide it by 4, and then you communicate it back. But think about, for example, a ResNet 50, which is a kind of state-of-the-art network for a couple of purposes, has 130 megabytes of gradients. If you take an old VGG 16 or 19, you're about 500 megabytes to 570 megabytes of gradients. So at the end, 570 megabytes delivered from 1, 2, 3, 4 GPUs, here calculated, and the average is built and then redistributed back for the next pass. This is basically causing those guys to do idling, which is not what you want. And so this explains why NVLink is a very important vehicle. So if you haven't understood why NVLink is there, this is the reason, because they create data that is distributed all over the place. And this is basically the all reduced step between the forward and the backward pass. If you want to stack multiple systems, as you've seen in the picture before, all those systems are typically equipped with InfiniBands. And this is going with direct RDMA over InfiniBand to build bigger rings.
May I ask a question? This bottleneck, let's say, going to the CPU, you're getting rid of a bit when using a power box. Is that right?
I come to that point.
Bandwidth, or But it's still only one CPU or slices of the CPU or the socket.
Here, the CPU has to feed them, right? Those are hungry chickens and they want to have data to calculate the next forward pass. If we do as in Keras, the gradient exchange via the same pass, we have basically a congestion here, and very quickly. So the gradient averaging has to go this way, and then you have your freedom to feed that one, right? So you're using what you have in kind of an efficient manner. But you need to do a little bit about it. He mentioned he did use Keras. Keras has a model to do it, but you can observe, if you're going to train it with Keras, then you can increase your batch size to the maximum, and then you basically see that the GPUs are used, not used, used, not used. So you can see this. And there's another way to avoid this. And we have a library. You also find it in our repository when you download CUDA and libqdnn, which is called NCCL. We typically refer to this one as nickel. And nickel is basically doing the dirty work in order to make sure this one communicates. But if you go on Keras or if you go on TensorFlow, you need to do a little bit about it. And I will tell a bit more about this one. There was a question that the GPUs in the IBM systems are attached via NVLink to the CPU. Yes, that's a very elegant thing because the system memory is not that far away from the GPUs than if you have a PCI attached system. So you have some more bandwidth and more flexibility on the communication. So that's a high bandwidth. You can see basically two NVLink lanes are used between the GPU and the power processor, and this gives you 150 gigabytes per second, which is pretty impressive compared to PCI. Now back, multi-GPU training. So what you should try next is to try Horovod. Horovod is a framework built by Uber. Uber also invests in self-driving cars. And the good thing is it's very usable. And in the background it makes use of MPI, it makes use of nickel, and it makes use of NVLink if you have so. So I have two slides to highlight a few things which you have to change. So if people haven't done deep learning yet, GitHub has a huge amount of nice samples. There are a lot of sophisticated ones, but if you say I want to learn something and understand it, take the less sophisticated because there's a lot to learn about this one. And you can basically say, I'm lazy. I don't need to do a CNN or network. Because at the top, you feed some image inside. At the bottom, you either get a regression or you get a classification out. Well, that's not a difficult API, right? You take a network which is doing this, and then you give it a try. And I was lazy as well. And for this one, I took a dense net. So, and my laziness was expressed in here. Do I have a pointer? Here, do I have a pointer? It's hard to see in the display, you cannot see it. Basically, it was import dense at SDN. It basically gave me that kind of, I need to tweak a little bit, but it's not so sophisticated. So here I didn't do any building of a neural network. And actually the internet is full of nice, good ones. So typically you take a network, you prepare your data, then you feed the data through the network, and it improves and improves. And here I want to just highlight using Horovod. And in line 4, we're importing the Horovod library. This is nothing sophisticated. And then in line 61, we need to do a HVD in it. So to get it set up. Then the more interesting stuff is happening down here below. So we have an optimizer. Recall every GPU is doing the same stuff. We have an optimizer per GPU, but then we need to collect all the gradients and do an all reduce. So we're basically then using an HVD distributed optimizer, which is taking the results of each individual one and giving me a result of the entire batch over all GPUs. Kind of easy. And Hoverboard is really something for, I would say, iPhone users. Its usability is key. There's another way to implement this in TensorFlow, which takes much more boilerplate. So I think even IBM has it in the pre-built software stack where we have it. So it's basically taking one of our Dockers, and I think it's exactly the same with where's Manteuffel? Jens, do you know this? Can you tell me?
I think they're not using the Automotive.
Well, at least I found it in your documentation. So this is basically the reason why I'm saying it.
Well, if you found the documentation, then you're probably right.
I simply was not sure about the vehicle you ship it to the customer. But if you want to do deep learning, there are three critical elements. You need hardware. We already know about Steffi. And then you need software, because you don't want to set up all this stuff. You can do it, sometimes it's fun, but if you want to do it on a regular basis, you better rely on somebody who is able to import or get nickel right, get MPI right, and things like this. So, hardware, software, and resources. Resources, we have Deep Learning Institute, but I'm sure there are bright people in the room you can treat as resources as well. And
we're not using Hoverboard. That's what I was referring to. You can have it run, but what's so special about Power AI, and what I think Stefan will talk about later on, is that we're using IBM-specific own mechanisms to achieve the same thing.
Okay, so you're saying we have the great usability, but we do it right. Right? Oh, this is enough for me. To get it complete, we need to do a little bit about sometimes. So when you have the mechanics of multi-GPU training right, when it works, then there are a couple of problems which drive you more into theory. It's called large mini-batch problems, and then all of a sudden you think, your batch size might be 32, right? Then you all of a sudden take 8 GPUs, your batch size, because each GPU has 32, sums up. So we have much more, and that can drive you in some strange behavior. But that's easy to cover once you know it, and because large mini batches behave a bit special. But let's separate that for the moment. Just focus on the mechanics. And because we have a lot of images, 2 megabyte images, our batch sizes are not that big, even with the latest Volta generation with 32 gigabyte of memory. You don't feed too large batch in a single run. So going multi-GPU, you still are away of those problems. But if you run into those problems, you basically adapt the training rate. You can do it in those hooks that fires on a regular basis, and you can adjust a couple of hyperparameters. You want a checkpoint written, but just by one worker, not by everyone, because if everyone writes into the same stuff, you can imagine how your book looks like if we write 4 people in at the same time. Doesn't make sense. So we limit it to the first worker. So this is if HVD rank, otherwise it's unset. And then, if you're familiar with TensorFlow, it has kind of a pattern. And typically with the train session, as a sesh, this is basically, you find it almost in every code base, changes a little bit to some hardware specific, but it's the same pattern. Monitor training session with some other parameters, and then the actual forward pass and the optimization, it's the same run, but we do it not counting up every to the epochs. We have chosen a different way of feeding the data into this one, which is a pipe. The moment the pipe dries out, we're going to stop. Now on the training, you want to kick off the job as often as you like. You kick off the jobs as with MPI run, And then you can define how often. Let's say you have a 4 GPU system, and you say 4 processes. All GPUs are on the same host, and you say localhost colon 4. If you want to train with 4 processors and you have a system with 2 GPUs each, then you would say server 1.:2, comma server 2.2. That means spin up 2 jobs on server 1 and the other 2. And then actually here we refer to the to this file. When you've done this, likely you're going to feel a bottleneck. And the bottleneck is likely that you don't get enough data in the system as you would like. And so you're starting to look into your data pipeline and make sure it performs right. There are a couple of things you can do. Session run with the feed dict. Feed dict is basically causing a lot of overhead because of copy and NumPy to TensorFlow conversion. So try to avoid this and go on TF records, which is a binary format. It blows typically your file up when you have, for example, pictures, because you don't read in a JPEG at that moment. You basically read in a decoded JPEG. But it accelerates the entire stuff pretty well. So with those 2 simple recipes, you've utilized your system pretty well. And you will experience speed up, which is not just, oh, it performs okay, which is really, well, I'm really surprised. So when we have POC customers coming to us, we make sure that we cover those points, because you've seen, I asked how many of you did multi-GPU training. I've seen one hand, and those few things have to be made to have an excellent product experience on the system, because our systems and the IBM 922 use it right. Otherwise, you have an 8-cylinder system which runs like a tuk-tuk. This is not what you want. Okay, call to action. Roll up the sleeves. Don't wait. Deep learning is not sophisticated. Deep learning is something for those guys, right?